Folks, it's sort of a sad day today as we begin our help videos on our final assignment for Unit 8, 8-20, Test Premier, the written part, Part 2. The first part of this, we had 25 objective questions. It is a Test Premier. On this part, we have a written set of questions to take a look at, and we'll have videos, several videos to go over these. And hopefully these will help you. As always, as we go over these, if you're still confused, do not hesitate to ask. You can email me any questions you might have, and I'll be happy to set up a meet with you or create additional help videos or email, whatever you prefer. But the goal here is to get help when you need it. In our first reaction, we're looking at a synthesis or direct combination reaction. That was one of the 7 types, where we have 2 reactants joining together to form one product. So when we do this, how do we go about doing this? Well, we have lithium, and we would write lithium right here. It says lithium, lithium's Li, and then we have oxygen. We write an O there. We look on our list of diatomic elements. Anytime we write an O, we put a 2 after it. So where did this 2 come from when we put these 2 together? When we put them together, we have a lithium joining with an oxygen to form a compound. Where do we get our subscripts? As we learned long ago, we will crisscross. Oxygen, or in this case, the oxide ion, always wants to be 2-. It needs 2 electrons. It's in family Roman 6. Family Roman 6 or group 16, they need 2 electrons to get 8. Oxygen has 6 valence electrons. When it gets 2 more, it will have those 8. So it wants to be 2-. Lithium's in family Roman 1, the alkali metals, group 1. They have 1 valence electron to lose to oxygen. So we go ahead and crisscross our 1 and our 2. So that gives us 2 lithiums here. We have 2 oxygens. So we need to put a 2 in front to get our 2 oxygens. You can't write the 2 here because that would no longer be oxygen. That would no longer be lithium oxide. We would have, if we write a 2 here, right after the oxygen, that would be lithium peroxide. That's not what we make in this reaction. So we put the 2 in front to balance out our oxygens. Now that gives us 2 times 2 lithiums. We need a 4 in front. And that takes care of reaction number 1. In reaction number 2, we have calcium reacting with water in a single displacement reaction, and there's 2 products that are formed. One, the aqueous product. We know one of the products is aqueous. The aqueous product will turn red litmus paper blue. It will also turn phenolphthalein pink. That is telling us that it is a base. Red litmus paper turns blue in the presence of a base. Phenolphthalein is pink in the presence of a base. Our base here is going to be the hydroxide ion. The other product is a gas, and it will cause a loud pop or barking sound as the gas is ignited with the burning splint. Well, that would be hydrogen gas. Hydrogen gas will combust readily in a burner splint. Now, how are we supposed to know this? They gave us some hints, but how are we supposed to know that those hints were leading us in this direction? Well, if you remember, we had several single displacement reactions to learn. Very first day we started this unit, we said there are reactions you simply have to know. In a single displacement or replacement reaction, if we have a metal here, metals will always replace the first thing written in a compound. So in this single displacement reaction, calcium is going to replace a hydrogen. H2O can also be written HOH. So this calcium right here is going to come in and replace that hydrogen right there. What are we left with when it replaces it? We see right here, we're left with the hydroxide ion. If a hydrogen ion gets knocked off water, you are left with the hydroxide ion. And calcium will take the place or replace that hydrogen. Where do these hydrogens getting knocked off? Where do they end up doing? They end up joining to form hydrogen gas. Now, where do we get the 2 after the OH here? Where did we get that? Well, calcium is 2+. The hydroxide ion, as we learned long ago, was 1-. Crisscross our charges. Why do I have a 2 after this H that was displaced? We go back up to Brinkelhoff. Hydrogen is the H in Brinkelhoff. Now let's take a look at balancing. We have 2 hydrogens here. We have 2 hydrogens here for a total of 4. So I need to put a 2 in front. 2 times 2 is 4. That gives us 2 oxygens. There's my 2 oxygens. If I have 2 hydroxides, hydroxides have 1 oxygen in them. So if we have 2 hydroxides, that would be 2 oxygens. We move on to reaction number 3. Now we are on a decomposition reaction. If you remember long ago, at the very start of this unit, we said that there were a multitude of decomposition reactions that we need to take a look at and to learn the pattern of them. And we actually saw this actual reaction take place on one of our decomposition reaction video demos. So in this reaction, we have potassium chlorate decomposing when heated. It goes best when we have a catalyst, manganese 4 oxide. So we write manganese 4 oxide above the arrow. When it's a catalyst, you write it above the yield sign because it's not actually in the reaction. And it says we need to heat this thing. There it is. We added heat. That goes above the arrow. Potassium chlorate. K is potassium. Chlorate is ClO3. We learned long ago that the chlorate ion is 1 minus. We already know potassium's 1 plus, crisscross our charges. Now what happens when the potassium chlorate decomposes? This is the one where the oxygens break off. None of the oxygens stay. This is the one where all the O's break off. So we have 2 times 3 oxygens for a total of 6 breaking off. So we have 6 oxygens breaking off. Those 6 oxygens will join up to form 3 oxygen molecules. 3 times 2 is 6. A lot of people say, why don't we write it as 2O3? We don't make ozone in this reaction. O3 is ozone. You make oxygen, the elemental oxygen, and O2 again. The 2 always goes after O when it's by itself in an elemental form. They would have to tell you that ozone was the product if indeed it was the product. Now, we saw in demonstrations how you can prove oxygen was released in this reaction. As chlorate decomposes, the oxygen comes off the chlorate ion. The Cl stays back. The Cl remains with the potassium. How did they prove that? Well, if you remember, we saw the rapid combustion of sugar. They throw Skittles into the test tube where this reaction happens, or gummy bears, a sugar product, into that. You remember that it ignited and burned rapidly. The other test is to take a splint and blow it out. If you blow a splint out and it has red embers and you insert it into the test tube where potassium chloride's decomposing, that splint will reignite into flames. So we already mentioned why we have a 3 in front there, but we would need to put a 2 in front here to balance out the 2 potassium chlorides, the salt that is left. We have time here to discuss another one of these on this video. And let's look at a neutralization reaction. A neutralization reaction of an acid, sulfurous acid, with aqueous potassium hydroxide. They told us it's an acid-base neutralization reaction. If you recall, acid-base neutralization reactions are a special type of double displacement reaction where water is the product. So in a double displacement reaction, when acid-base reaction is the one we're talking about, water is the product. Sulfurous acid, where do we get that? Oh, this is a nice review on naming acids. With sulfurous acid, it's an us acid. Us acids end up producing the ite. Sulfite ion is the ion that comes from sulfurous acid, lighthouse. If this was sulfuric acid, then we would write the sulfate ion. I ate it, it made me sick. So sulfite, if you remember, is SO3. Sulfite's charge, same as sulfate, is 2 minus. It is 2 minus. The hydrogen ion that's going to get kicked off this acid is 1 plus. 1 plus. So when the polyatomic ion is a 2 minus, we cross that 2 down. We would need 2 hydrogen ions, or we'd need 2 hydrogens on there. Potassium hydroxide, where do we get this formula? We learned that the hydroxide ion is 1 minus. Potassium, being an alkali metal, can only be 1 plus. It only has 1 valence electron. We crisscross a 1 and a 1, we end up with KOH. So what happens in this reaction? Sometimes it's easier to write it like this. This is a double displacement reaction. This hydrogen right here is going to trade places with that potassium right there. In a double displacement reaction, the first thing exchange places. This is why some people call it a net ion exchange. Hydrogen is going to exchange places with the potassium. So the H joins up with the OH in this reaction. That's why over here we wrote HOH. There's the green hydrogen coming off. Here's the OH coming off this side. Joining with that green H, we have HOH. We have 2 hydrogens coming off, and there would be 2 OHs for them to join with. So we would end up making 2 waters. HOH can be written as H2O. What is our other product here? Well, we said the K here, the potassium here, is going to leave and join up with the SO3. The first thing here joins up with the second thing here. The K trades places with the H's. The K trades places with the H's. So there's the K. It takes H's spot. There we go. The K's now with the SO3. If it's written first on this side, it will always stay first. SO3 is second here, so it will say second. Where do we get our formula for this? Well, the sulfate ion, as we know, is 2 minus. It stays 2 minus. Potassium's 1 plus. It stays 1 plus. Crisscross. So they have a 2 there. That 2 comes down here. Glad we have that 2 in front. 2 of those. That gave us the 2 OHs as well. We only have 1 SO3 there, so we would not need anything in front of that. Let's do one more on this video. We'll shut it down. We're going to be able to finally get to balance a combustion reaction. And they're combusting butane, which actually is a liquid. It goes to a gas very easily. The combustion of butane. In balancing this, it is a combustion reaction. Remember the Hollister rule. The Hollister rule, the acronym for Hollister Company, is HCO. Hollister rule tells us that we're going to do the hydrogens first. When we write a combustion reaction, we have our butane, C4H10. But in organic speak means 4. Combustion reactions are going to involve oxygen, and the result of the combusting a hydrocarbon is always carbon dioxide and water. Those are always our products. So now let's go Hollister on balancing these things. Hydrogen is first. We have 10 hydrogens there. So initially we're going to try to put a 5 in front of the water. 5 times 2 is 10. However, if you remember, we cannot put an odd number in front of the water because that would give us an odd number of oxygens. 5 times 1 would be odd. We look over here, we can never have an odd number of oxygens. So we double it to make that 10. 10 times 2 is 20. So we now have to put a 2 in front of this. 2 times 10 is 20. Hydrogen's done. We now go on to carbons. 2 times 4 carbons is 8. So we have to put an 8 in front of the carbon. 8 times 1 in front of the carbon dioxide. 8 times 1 is 8 carbons. And finally, we go to our oxygen, leaving it for last. 8 times 2 oxygens is 16. Plus 10 times 1 is 10. 16 plus 10 is 26. We need a 13 in front. We're going to stop here with these first 5 reactions on video, our first video over 8-20, the written part. We'll continue on in other videos with the rest. Thank you for watching.